Okay, welcome. This is a review for the upcoming Unit B test. I'm going to say pause every once in a while. That's when you should pause the video and try and answer the question yourself. And then you can check your answer. Okay, let's see how this goes. This is the first time I've ever had a review like this before. Let's start out with a friction question. You have a box on a horizontal surface. It's 2 kilograms. The coefficient of static friction is 0.3. The coefficient of kinetic friction is 0.2. I'm going to come here and push on this with 1 Newton of force. And the question I have of you is, what will be the force of friction when I push on that with 1 Newton of force? Go ahead and pause. Okay, so now we're back. And the way you figure this out is you first have to find the two forces of friction, static and kinetic. So to find the force of static friction, the max it's going to be is going to be 0.3. You use the coefficient of friction times the normal force. Now the normal force, since this is 20 newtons down, the table must be pushing up with 20 newtons. It's the 20 newtons the table's pushing up on that you put there. So that's 20 newtons. If you do the math there, that looks like it's going to be 6 newtons. That's the maximum force of static friction. Okay, the kinetic force, well, the kinetic force of friction, I'll get to in a little later. But if I push with 1 Newton, if you thought that this was going to be 6 newtons pushing back, then that means the box would actually head to the left. No, what it is that it will match it Newton for Newton, so that will be 1 Newton. If I pushed on it with 2 newtons, this would be 2 newtons. If I pushed on this with 3 newtons, that would be 3 newtons. Okay, my second question then is, what if I came in a little while longer, I came and I pushed on it with 10 newtons. This time I'm going to push with 10 newtons. Go ahead and pause. Well, go ahead and pause. Okay, we're back. So now I'm pushing on it with 10 newtons. That's bigger than 6 newtons. And so because of that, the box is going to actually move. The box will start to accelerate that way. Which means that if it's moving, I can't use 6 newtons for the force of friction. The new force of friction is, I got to use 0.2 for kinetic friction times the normal force, so 20 newtons. So that gives me 4 newtons of force. So this will be 4 newtons of force. Hey, if that's 4 newtons of force, even if I pushed on this with 100 newtons, this would still be 4 newtons of force. The force of kinetic friction doesn't ever change. So what would be the acceleration of this box? This is not a question for the review. Well, it is a question for the review. The acceleration of this box would then be the net force, which is 10 newtons minus 4 newtons, all over the mass of the box, 2 kilograms. So that would be 6 newtons divided by 2 kilograms. I'm thinking that that box will have an acceleration of 3 meters per second squared. Okay, on to the next topic. Okay, if we have an object that has a momentum vector that varies with time according to this equation, that would be 4 kilograms meters per second to the 4th t cubed in the I direction plus 10 kilograms meters per second in the j direction. Could you tell me what the force is 2 seconds at a time of 2 seconds? So the question is, what is the force at a time of 2 seconds? Okay, pause. Okay, we're back. Did you get this? You got to take the force is going to be the derivative. It's the derivative of the momentum vector with respect to time. So if you take the momentum vector's derivative, that's going to be 12 kilograms meters per second to the 4th power times t squared. That's in the I direction. in the j direction, it's going to be, that's a constant, so that when you take the derivative of a constant, you get 0. Go ahead and put in 2 seconds then. When you put in 2 seconds, notice that what we get is 4 seconds squared, and so my units are going to be, well, I'll get 48, and that's going to be kilograms meters per second squared. That's the same thing as 48 newtons. Well, there you go. Okay, next topic. Oh, one other comment on that. If you're wondering why it's the derivative of P with respect to T, let me quickly show you. You know how the net force equals MA? Well, the net force then is equal to M times the derivative of V with respect to T. Isn't that A? This is A. Okay, well, if that's the case, let me put the M, which is a constant, let me go ahead and put it in the derivative. So that's okay, you can do this. You can throw a constant into the derivative if it's on the outside. And when you do that, that's just the momentum. So that's why it's dp dt. All right, going on to the next one. Potential energy. Let's say you know an object's potential energy function. It looks like that. It's 4 joules per meter cubed times x cubed. If I wanted to know the force that goes with this at 2 meters, what will be the force at 2 meters? Okay, go ahead and pause. Okay, we're back. The force is going to be equal to the negative derivative of u with respect to x. And so if I take the negative derivative, I'll put a negative there so I don't forget it. That's that negative. And now I take the derivative of this, it's going to be 12 joules per meter cubed. The units just stay the same always with all this stuff. Times x squared. So what is the force? It's going to be, if I put in a 2 meters, then it's going to be 2 times 2 squared. 2 meters squared gives me 4. So it's going to be 48 joules per meter. That's what the units are going to be. But a joule is a newton meter. So that's 48 newton meters over meters. So the meters cancel. And so that's 48 newtons. See how that works? Okay, I have time for one more. Try and get all this in 2 reviews. Okay, so you got the force on a spring. I want to know if this is the force of a spring and it's stretch. This is the stretch. What is the force constant of this spring? Go ahead and pause. Okay, the spring constant is the slope of this graph. So the slope is equal to K, which is maybe 20 newtons. There's a few ways to do this. 20 newtons over 0.2 centimeters, or 2.2 meters rather. You got to put it in meters. And so that's going to be 100. That is going to be 100 newtons per meter. Is that right? Yeah, I think it's 100 newtons per meter. Okay, then lastly, I'm going to ask, what is the amount of energy stored in the spring when you only stretch it 10 centimeters? When you only stretch the spring 10 centimeters, what is the amount of energy in the spring? Okay, go ahead and pause. Okay, we're back. That would be the area underneath this curve. So the area is the energy. And that's going to be equal to 1/2 the base, 0.1 meters, times the height, 10 newtons. Okay, I'm out of time. I'll see you.